this is number 58 on page 231. A small block of mass, 0.5 kilograms, is fired with an initial velocity of 4 meters per second along a horizontal section of frictionless track as shown at the top portion of the figure here. This picture right here is also in your book. The block moves along the frictionless semicircular vertical track with radius r 1.5 meters. Determine the force exerted by the track on the block at points A and B. All right, you'll notice this is a semicircle with radius r, and we know from here to here it's going to be 1.5 meters, and from here to here is going to be 1.5 meters. And so the initial total energy of this thing is going to be kinetic plus potential. So it's going to be 1/2 times 0.5 kilograms times how fast is it moving, 4 meters per second, plus 0.5 kilograms, that's mgh is what I'm doing here, times 10, that's meters per second squared, I'm about out of room, times 3 meters, because 1.5 plus 1.5 is 3 meters. So with respect to B being 0, it has this much energy, which is going to be 4 joules plus 15 joules, which equals a total energy of 19 joules. But only 4 of that is kinetic. Only 4 of that is kinetic. So when it gets to point A, I've got to know how fast it's going, because if I look at a force diagram here, I'll draw this kind of big. It's got mg pointing down, which is not going to have anything to do with the centripetal force because it's toward the center. The only thing pointing toward the center is the normal force. In other words, the wall is providing centripetal force. Otherwise, it would go straight and just continue on to the right forever and ever. But because of this wall, and the wall puts normal force on it, it's got centripetal force. So I've got to find the velocity at A, because the normal force is causing a centripetal force, which is m v, and this is going to be the velocity of A specifically, squared over radius of 1.5. So I know everything in this equation but VA. So what I've got to do is say kinetic energy 4 joules, that's what it starts out with, and then 15 joules of this potential is added, not all 15 joules, but some of the 15 joules of potential goes away and turns into kinetic at point A. So it's going to be plus mgha, which is going to be 0.5 kilograms times 10 meters per second squared times 1.5 meters. And when I do all of that, I'm going to get a total energy of 11.5. So now my E kinetic, which is kinetic, instead of being 4 joules, is 11.5 joules. So all I've done is I've changed this much potential into kinetic, so that now I've got 4 joules plus 7.5 joules, which is 11.5 joules of kinetic, which equals 1/2 mVA squared. I'm going to let you guys plug that into the equation, but you should get VA equal to 6.78 meters per second. VA squared is going to be 46, basically. So the first part is Fn equals 0.5 kilograms times 6.78 squared is 46 meters squared per second squared, all divided by 1.5 meters, and I get 15.3 newtons, which rounds to 15. That is A. That is the A part. The B part, actually, they asked for two parts on A. So that's the first part A. The second part of A is what is the hold on, determine the forces are on the track. So now I've got mg down, Fn up. So now I've got two forces. This is still going in a circle until it gets way past B. It's still considered centripetal. So this is going to be Fn minus mg equals mv squared over r. This is going to be Vb. So Fn is going to equal mvb squared over r plus mg. All right, so I know everything in this equation but Vb. So now I've got to figure out the velocity of the block at point B. Well, I already know the total energy of this whole thing is 19 joules right here. So when it gets to point B, all 19 joules is turned into kinetic, all 19 joules. Before it was 4 joules of kinetic and 15 joules of potential. But when it falls from here all the way down to B, 4 joules is still kinetic, plus the 15 joules that was potential is now kinetic. It's all kinetic, which is 19 joules. So I just say 19 joules equals 1/2 mv b squared. I'll let you guys do the math, but Vb squared is basically 76, or V is equal to 8.72 meters per second. It's probably rounded values. Okay, so now I'm going to say Fn equals 0.5 kilograms times 8.72 squared is 76 meters squared per second squared over 1.5 meters is still that's kilograms of 0.5, plus 0.5 times 10 is 5 newtons, and when you do that you get 30 point something, like 3 or 2 or something, and that's our answer. Just rounds off to 30. That's our answer for the A part. That's how you do the A part. Alrighty. So what's the B part asked? The B part, the bottom of the track consists of a section of that's length 0.4 with friction. Determine the coefficient of kinetic friction between the block and the portion of the track if the block just makes it to point C. So if I go back up here and look, basically this thing has to make it all the way here and just barely be moving. Well, I shouldn't say that. Moving just fast enough so that the normal force is 0. In other words, it's going to lose contact with the track. So that's what will cause it to barely make it to point C. So to do that, I've got to do a couple of things. I've got to figure out the velocity. Let me do this in a different color. So this is part B. So I've got to find the velocity at part C such that the normal force is 0. Well, when it gets up there to part C, if we just draw a little diagram, there is mg down and Fn down. If Fn, though, is 0, then all that's providing my centripetal force is mg equals mv squared over r. Vc would equal the square root of gr, and that's going to equal about 3.87 meters per second, a little less than 4. So it's got to be moving at 3.87, not faster, not slower. And so at point C, when it gets up here to point C, looks like this, then I know the velocity is 3.87. So I need to know the total energy here. The total energy is going to be the potential plus the kinetic. Well, the potential I already know is 15 joules, joules. I know that because it was 15 joules up here someplace where we did mgh, where h was 3 and you got 15, and then you added 4 and you got 19. But now I'm not going to have 19, I'm going to have 1/2 m times 3.87 meters per second squared. When I do that, I'm going to have 15 joules here plus, I think this comes out to 3.74 joules, and that's going to give me a total of 18 point, we'll just say 18.7 joules. Well, how much am I missing? I'm missing about 0.26 joules if I subtract 19, because remember my total energy was 19, but I only have 18.7, which is about 0.2, maybe, is that 2.3? I think I did my math wrong. Hold on a minute. 19 minus 18.7 is 0.3 actually. So I'm not sure I got 2 point. So hold on. This is 0.3. So when I subtract 19, I get 0.3 joules. All right, well, guess how much energy friction has to take away to get it down to 18.7 instead of 19. It has to take away that much. So the work of friction has to equal 0.3 joules. Well, what's work? Work is force times distance. That's joules, which equals, frictional is the only force, times distance L. So 0.3 joules equals mu, which I don't know. Fun equation, remember, normal force is going to be 5 newtons, and L is going to be 0.40 meters. So basically 0.3 divided by 5 divided by 0.4. So 0.3 divided by parentheses 5 times 0.4 in parentheses, and I get 0.15. And I think the book got 0.17, but I rounded. I used 10 instead of 9.81, so same thing. So there's your answer to that last part, 0.15. Is that the last part? Yep. That's how you do number 58 on page 231.